you very much. Wow, we'll start having a lot of participants here. So that kind of bodes well for the hands-on session if we have like that many for the introduction. I will make an introduction to the hands-on session on the disk models. The session will happen tomorrow. And what I will do right now is I will give you some information and some background on the science, on the underlying science, what you're going to do, how you're going to do this, and the specific logistics of this hands-on session. In particular, so a lot of what I'm going to talk to you about in this talk is actually part of the documentation PDF that you have downloaded, hopefully. And but I also realized that there are lots of you who are brand new to exoplanetary science, and I took a look at some of the questions that were being asked, for instance, like this morning in the Q&A, and I realized that there are lots of you who may not be familiar as much as some others to some of the concepts that we're having here. So I would try to be extra careful for you guys and try to explain to you all the concepts in a maybe more in depth than what it is in the documentation. Okay, so let's go. So in this hands-on session, we will introduce you to circumstellar disks. So you've heard a little bit about those in Carl's talk this morning in the roadmap. He cited a little bit of all of the kind of disks that you're going to encounter during this meeting. And we want you to understand how we people who do exoplanets and study disks, how we study those, how they can appear at different stages of their evolution and the different kind of feature they can exhibit. So basically, there are two main tools that we use to study disk. We use, of course, images. Okay, so this is historically the very first image of a debris disk that was taken. This is the debris disk of Beta Pictoris in 1984, but we also use spectral energy distribution, and spectral energy distribution represent how bright a source is as a function of wavelength. And I would like to give a precision here because I think I saw this question this morning and someone was asking, why do we have here the flux multiplied by the frequency on the y-axis? And the reason is because when you make measurements of flux of a source to build this spectral energy distribution and have data points, what you're actually measuring is what we call spectral density, spectral flux density. And we usually say flux. It might be a little bit of an abusive language, but what you measure will be in watts per square meters per hertz. And so the fact that if we multiply here by the frequency, all fluxes are in watt per square meter, and the graph looks much better because, as you can see, we cover like several decades of wavelength and hence frequency. And so if we do not multiply by the frequency, the fluxes here will appear much smaller. So we have everything in watt per square meter. So I hope this kind of answers the question we had this morning. Spectral energy distribution were historically the first tool that was used to detect disks. We did not get images straight away. What we got actually were spectral energy distributions. And so this is what we call the Fabulous Four. They were seen with IRAS. I don't know what the publication is, 1993. I think like we got them before the images actually, but so basically what happens is when a star is surrounded by a debris disk, a circumstellar disk, I'm saying debris disk is a little bit because I'm doing debris disk mainly, but when a star is surrounded by a circumstellar disk, the dust or the gas will just absorb the starlight, and you will re-radiate the energy in the infrared. Well, the dust will absorb the starlight and re-radiate the energy in the infrared. And so what happens is when you plot the flux as a function of the wavelength, you have your star. Here is the tail of the star spectrum here, and this is what you expect it to be. But instead of having something that follows these lines here, there, you have your measurement points are above the level that you would expect, and this is called an infrared excess, and that tells you there is dust around your star. So a great number of disks were revealed with IRAS and plenty of other facilities later, ISO, Spitzer, Herschel, and the list is certainly not exhaustive there. So this is one of the tools that we use to detect and characterize disks, but we also use images. So here I'm showing you images at optical wavelength. So at optical wavelengths, so that is visible wavelength, the images that you will see will reveal micron-sized dust grains, because these ones will reflect the starlight at these wavelengths, okay? We're not in the infrared just yet. It's not a question of absorbing and re-emitting. In this very case, they're reflecting the starlight. And so these are exquisite images of debris disks that were taken with the Hubble Space Telescope of Beta Pictoris and Fomalhaut. Again, two of the fabulous four, the first disk that was discovered. And these ones actually are debris disks, but I will tell you about the distinction between debris disks and the rest later on. So Hubble is in space, and now we have facilities on the ground that enable to image debris disks or disks as well at optical wavelength, at scattered light. So there's GPI and sphere. And just a rule of thumb that I would like you to remember is that in general, a wavelength reveals dust grains of similar sizes. So at optical wavelength, you will have this micron-sized dust grain that will reflect the starlight, and later on at longer wavelengths in the infrared, there will be absorption and re-emission. But in general, if you're studying something at 10 microns, you can expect having grains, revealing grains of tens of microns in size. And so here, if you go to longer wavelength with just, let's say, Herschel, here you have an image of Vega at 70 microns. So like I was saying, here you have bigger grains, several tens of microns that are being revealed. And here are other facilities, the GCMT, the James Clerk Maxwell Telescope, and ALMA, which Carl introduced in his talk. And here you're having grains of several hundreds of microns and millimeter size that are being revealed. And so we kind of like, me especially, I don't know, debris disk community in particular, like really like this kind of images at longer wavelengths, because what happens is that you see big grains. So if you have a planet imprinting patterns in your disk, you're more likely to see it at this wavelength, because the smaller your grains and the more they will be sensitive to stellar radiation effects. And so they will be all over the place. Like, for instance, if you see here with Fomalhaut, they're all over the place. But here the same image of Fomalhaut with bigger grains, and these are like very much confined to a narrowing. And so, yeah, obviously you can learn a lot on a given disk from images. You can learn whether they're very extended, very broad, or very narrow, how distant they are to their star, if there is any asymmetry in there. But a lot of the time, detailed images are not really easy to obtain. And I'm thinking in particular for debris disks here, because this is what I mainly do. But in this case, this is kind of difficult. And it takes, for instance, it takes several hours of ALMA time to get a nice image like that. So there are lots of things that you can already learn from SED. And what we want to do is that we want you to understand what kind of information you can retrieve from an SED. And we want you to understand how sometimes different phenomena can have the same kind of effect on your SED. And this is a problem. This is not really confined to the field of exoplanets. I think it's much more general to any kind of field in physics, is the concept of degeneracy. You have a piece of information, but you cannot really know what this little piece of information is telling you, because you have different things that can give you the same piece of information. And so sometimes you need a complementary piece of information, something obtained from with another tool that can help you break this degeneracy. And so this is what we want you to have a feel for during this hands-on session. We want you to understand that sometimes SEDs can give you like some clues at what is happening, but unless you have images, you can't really know for sure what is going on. And so we have chosen 4 objects that will represent different evolution stages of disks. And for each of those, we have chosen a couple of significant parameters, and we're going to have you explore the kind of impact it can have on images and SEDs. And so here are in the order this is the time goes from left to right. So you have HL tau. So HL tau is this beautiful disks with gaps in there that was revealed by AMA, but HL tau is surrounded by an envelope, so it makes it still very young. And if you want to know more about that, you can see again the talk we had this morning about this. And then we have HH30, which is a T-Tauri star, and then PDS70, which is called the grown-up, and finally HR4796. And I'm going to give you a little bit more details about each of these objects right now. So we had a very nice talk this morning explaining to you that stars are born in molecular cloud cores, and they are surrounded by large envelopes of dust and gas, and how the envelope will fall onto a disk and will be accreted onto a star. And this is exactly the case of HL tau. HL tau harbors a protoplanetary disk, but it is surrounded by a very large envelope. So we would like you to explore the effect of the envelope mass on SEDs and images in this hands-on session. So here is an image of, so the little disk I showed you before, this little, and here, it's actually this tiny, tiny thing just right there. And in green here, you have what can be seen with Hubble. And you also have AMA bands that show gas. So you can see that the envelope is quite large around here. And of course, AMA pierced through the envelope, and it revealed that the largest grains in the disks harbored a series of gaps here and had settled in the midplane. So I will refer you to talks that we're having tomorrow, and you will learn more about grain growth, so how grain grow in a protoplanetary disk, and how the bigger grains settle in the middle. But this is something we learned for HL tau. And what we want you to explore as well with this system is how the presence of gaps affect the SED, whether you can maybe know whether there are gaps already from the SED or not. And we also want you to understand the effect of the disk scale height. So the disk scale height is a measure of the vertical extent of your disk at a given, you have a reference distance. Usually, in this case, it will be 100 AU. AU meaning astronomical units. This is in general the unit we use to explore exoplanetary system. 1 AU is the distance between the sun and the Earth, and it's general is the unit we use because a typical planetary system will extend over several tens of AU in total. And so we want you to explore the effect of the disk scale height. So what is its vertical extent, and the presence of gaps. And Then HH30. So HH30 is the next evolutionary step. It's a T-Tauri star, and in that case, the envelope is depleted, and you have an accretion disk. And this accretion disk looks like, depending on how you see that, maybe a macaroon or a hamburger. But what you're having here is a disk that is flared. And I told you that big grains are generally settled in the mid planes, but the small grain distribution appears flared. And so, no, I don't have. Okay, I'm going to get back here. So basically, I was telling you the vertical, the scale height is the vertical extent, so it measures how big your disk is in the vertical direction, and the flaring measured this curvature that you can see here, how much curvature you have there. And so we know in the case of HH30 that it is a flared disk. And here, I really like this image because you can see this is a superimposition of an image at optical wavelength. So if you remember what I told you, optical, you will see small grains, and you can see that the distribution of small grains is flared. The disk is seen edge on. And here you have superimposed an image seen with ARMA, and you can see the ARMA reveals the bigger grains, and they are settled in the mid plane. And here's another image, and you can see there's actually a jet coming out here. And so for this system, we would like you to explore the disk flaring index, the effect of the different curvature on images in SEDs, whether you can actually measure that already from the SED or not, the dust mass in your disk, and also the inclination, because this disk is seen edge on. So we would like you also to have a feel for what happens when you see a disk at different inclinations. The next disk that we propose you to study is that of PDS-70. So after protoplanetary disk, well, I'm not sure. I think actually whether a transition, it's called a transition disk, but I think it's still a debate whether it's an actual transition right after the protoplanetary and before the debris disks. I think there are people who are much more indicated than me to answer this question. I think Nienke van der Mare is attending, and she might be able to answer that much better than I do. But basically, a transition, what we call a transition disk, is characterized by the presence of a large central cavity. And it might be carved by some combination of stellar wind, radiation pressure, grain growth, accretion on the star, and maybe also forming planets that will clear their path. And so here it is a transitional disk with the full cavity. And here's what's called a pre-transitional disk, where we're still having a little component here close to the star. And you can also see it here in the artist view right there. And so PDS-70 is surrounded by a pre-transition disk. So you still have a little component close to the star. And between this close component and the rest of the disk, there's a giant gap that extends from 1 to 60 AU. And just to give you an idea, so 1 AU is the distance between the sun and the Earth, and 60 AU is typically somehow the distance of the solar system's Kuiper belt. So imagine there's just a giant gap in between. And 2 planetary mass companions were detected within the cavity. This is, I think, why the system is most renowned for. And so with this one, we want you to explore the effect of the gap width. So here, the gap is about 60 AU wide. So we want you to explore the effect of a gap having, like, I don't know, 50, 40, 30 AU wide. We want you also to explore the effect of the gap depth. So how populated it is, how empty the gap is, and also the presence and temperature of a planet, whether you can already see a planet in an SED or if you need an image to see this, and what the temperature of a planet will, how it will affect your images in your SED. And finally, after a few million years, so we're all talking about disks that were still containing a good amount of gas. And after a few million years, the gas in the disk is dispersed and the star becomes a main sequence star. And what you have left is what's called a debris disk. So this is my own personal specialty. And these are analogous to the object that was first discovered by IRAS, which I showed you, the fabulous forward debris disks. So these are much less massive than a protoplanetary disk because you have little to no gas. And the dust that you see in there is not first generation. It's not something that is remnant from the molecular cloud. It's second generation because you had all the process of dust growth up to the point where you have kilometer-sized bodies, and why not planets? And these kilometer-sized bodies, which we have analogs in the solar system, like asteroids or comets, they will collide and they will be in what we call a collisional cascade. And so it will form smaller and smaller dust grains. We're going the other way around. There was this whole time where you had grain growth and you go to these large bodies and then you go the other way around and you just produce this little debris. And so we have chosen HR 4796 for this. This is a ring that is quite narrow, similar to Fomalhaut that I showed you earlier. And it's perhaps supported by one or more planets. We still do not know for the system. And what would like you to explore for the system would be the radial location of your narrowing, so varying the radial location of your ring, and also the dust grain size that you're having in your ring, and how it affects an SED, if you can have any info from the SED or you need images. So basically, yes, you will investigate science questions of the following type. What can an SED tell me about this parameter for a specific system? And what do images tell me about the same parameter? And is the SED sufficient for me to know about this? Or do I need to break a degeneracy and need images for that? Or and is there an underlying physical phenomenon at play? And so here are snapshots from the documentation. So in the documentation, you have this table here that will summarize all the properties that we want you to explore and which object allows you to explore those. And also the questions for each object are summarized in this colored question box. We also have gathered all these questions in a multiple choice Google form. And so we will make this accessible to you while you're doing the hands-on session. So yeah, everything I just told you and much more you can find in the documentation, and you can have the link from the hands-on session page. So now, what's going to happen concretely? Where do the SEDs and the images that you're going to work with come from? Well, we will provide the outputs of a radiative transfer code called RadMC3D. So it's a code that you give. I have a star that is that bright, and I have dust with these grain sizes, and that extends from there to there, that's mass, etc. And it will compute how starlight is either reflected or emitted with thermal emission. And what we want you to do is to use a Python library that has been developed to process the outputs of RadMC3D to plot these SEDs and images. So now, we had to make choices and to produce these outputs, it can take a significant amount of time. So just to install the RadMC3D code completely itself, you need additional installation processes. You need a Fortran and a C compiler. And so it might have been a little bit more complicated than just having you go through the outputs. In addition, some of these outputs can take a long time to compute. And so if you're just spending most of your time during a hands-on session waiting for an output, and you produce just a couple of those in 1 hour, this is not the best use of your time. So we decided to produce the outputs beforehand and then have you go through those. So a little note here is that for each of the discs, and that's on me, I've been calling those best fit. So there are things that are being called best fit and from which you are going to vary the parameters. This is more actually a nominal model than it is a best fit. We did not go through the an actual best fit process. We just tried to get as close as possible to a disk that we could, so that we could see the effects we wanted to see. And then from there, we varied the important parameters that we wanted you to explore. So whenever you see best fit, it's actually more of a nominal model. And so concretely, you will either use Jupyter notebooks or Google Colab notebooks. So please refer to the hands-on session website. In either case, you will need a bit of time to install what you need to install. If you choose to go through the Jupyter notebooks, you will need a Python installation. And if you want to go, if you do not want to install Python for whichever reason, you can go through Google Colab. You don't need a Python installation for that, but you still need to set up the notebook. So please, if you intend to participate to the hands-on session and you haven't done so yet, refer to the hands-on session website. You have all the links that you need there. It takes about half an hour, but it would be a shame for you to arrive tomorrow and spend like half of your time installing this. And if you're encountering any difficulty with this, do not hesitate to take a look at the Python help Slack channel. There are some little problems that are already known. So some people already bumped into those and we've already answered their questions. So you can either take a look at that, or if you can't find anything that relates to any of the problem you're having, please reach out to us. And we're having fantastic people already helping there. And I just want to shout out to them because they've been helping a lot. And so there will be one notebook, either Jupyter or Google Colab per disk, and you will work through it cell by cell. And so this is how it looks like. You have a cell here with pre-filled code, and that produce a plot. And so whenever we want you to explore a parameter, you have a set of files with different names. In general, it's just a value for a given parameter that changes in the name. And you can either directly change the name of the file in the pre-filled code cell, and have a brand new plot, or you can create new cells if you're a little bit more familiar with Python. And I know a lot of you are not really familiar, so that would be a good chance for you to actually get your hands into Python. So you can create new cells and copy paste the code and modifying as you wish. You can modify the axis, you can modify lots of things. And that's the same for the images. You have cells like this, and you can create new cells or just change things in the cell directly to change your image there. And so I was telling you about a Google form with multiple choice questions that we have put together. And the link to this Google form would be at the very bottom of each notebook. So you can fill it out several times. I mean, like I'm saying, there's just one notebook per disk. So if you arrive at the end of your notebook and you open the Google form, of course, you're not going to be able to answer questions for the disk you have not seen. So skip the questions you cannot answer and just answer the ones you can. And after you submit, you will see the answer key for the question you submitted. And you will be able to submit again for if you are going and studying another disk, you will be able to fill out the questions for this disk when you reopen the Google form the next time on the next notebook. So the live hands-on session happens tomorrow. I myself and Elise Ferland will be the leads, and we have a wonderful team of volunteers, and you can see their names over there, and you can see that each of them has an object that is associated with them. And so what we will do is that you will be assigned randomly to one of the 9 breakout rooms. So each room has a primary object that is assigned, which means that this is the object on which you will start working. And you can use the Zoom chat function to ask questions to your helper, or whichever way I don't know exactly how many of you will be in each Zoom. So it might be better to, I don't know, use the chat function, or to ask your question directly to your helper. And most importantly, if you finished working on the object assigned to your room, don't change room, change object. Your helper are trained to help you on any of the objects. But yeah, don't change room, because depending on how many you will be, it will be kind of difficult to channel you, to have you come back and channel you again toward other room. If you cannot, well, I mean, if you have not done everything during the live session, or simply you cannot attend the live session because your time zone does not allow it, we will be here throughout the week to help you. Okay, so you can use, well, the documentation. You can use Slack to ask your questions. So please use the Python help channel for everything related to installation, and there's a hands-on session disk for everything related to the science questions that you might have. We have the multiple choice Google form also, because it's a multiple choice. Sometimes you can have some clues at what the answer will be. But also we have a hands-on lab in Gather that was put together. So if you want to meet there with a couple of people and just work together on your own time on the notebooks, you can. So this is a screenshot of the hands-on lab. You have big table, small table, and each of this table is a private space, which means, like, for those of you who haven't been on Gather yet, as soon as your little character goes to one of the table, this table is a private space, and if you have anyone joining you, you have suddenly kind of a little Zoom that opens for you, and you can chat live. So that gives you that makes up for the fact we're not meeting in person, and that gives you a more like lively experience on that. So you can go there anytime. I myself will try to be around there in this room if anyone needs help. I think some of the helpers will too. You can use also Slack. And well, at the end of the workshop, what we will hand you a complete documentation. So right now, the PDF you're having stops with the question boxes for each object, but of course we will provide to you all the detailed answers to the questions, and I will also make sure that in there you will have the input comments for RadMC3D. So the ones I use to produce the models you will explore, in case you find this very interesting and you want to use the code yourself, and you want to run models yourself. I will put the input comments in there in the complete documentation, and we will hand this to you at the end of the workshop. Okay, well, I'm a little bit early, but I think that's all for me, and we really hope you will enjoy what we've prepared for you, and that you will have a pleasant experience. And well, I'm here for questions.
Yeah, I don't think we had that many questions on the Q&A. They're mostly about the science and so on, but it's a lot of things they have to figure out on their own. Maybe one thing, right? The slides will be available. You make the slides available on the website. So these slides that you showed right now
will be available, and the talk is being recorded right now, isn't it?
Yes, it's just that the talk recording might not be available before tomorrow.
Okay, I see. Okay, I don't think I've sent you the slides yet, but I can do that ASAP.
Yes. So we'll put the slides on the website, so at least can see the slides, and the recording, it takes a while for Zoom to process it. So that's just really a limitation, that Zoom takes a while to get the video to us. And one thing about the Zoom meeting, maybe to point out, right, that it's a separate link, and that will be emailed later today and also put on Slack. So just for the hands-on session activity tomorrow, 12:45 to 1:45 Pacific, so it's the last item in the agenda, there will be a separate Zoom meeting. It's just something that I know it's a bit confusing. So we have the webinar for almost everything except for the hands-on activities, hands-on sessions, Zoom meeting, and the Zoom meeting link will be emailed and put on Slack. Yeah, I don't know if there's anything else in the Q&A, I think.
It looks like there's one question. It says, hi, since the models have already been run for us, is there a place we can see what input parameters were used to create these models besides the ones we are varying?
I haven't done that yet, but it will be in the final documentation. Absolutely. But and also in the documentation, I've put some information on the parameters I used to produce the models. I don't think I've been exhaustive, but yeah, I think I've given indication of what I've been using. I'm not entirely sure I've been totally exhaustive on what I've been putting in there. But there are some informations already in the documentation, and the final documentation will include all the input comments that I used, so that you will be able to see that.
And there's one more question about if there's only dust included in the RAD-NC or gas as well as input.
Well, with gas, you will see gas lines. So we haven't been producing anything with gas lines. No, we have not.
Okay, and one question which you're probably going to address is, will the parameters, envelope mass, scale height, and so on, all be obtained through model fitting? How do they degenerate with each other?
Well, that's a good question. You have to attend the hands-on session and try to have a feel for this.
That's your job, right? Yeah, you're the attendees, not yours, Virginie. Yeah. And and so after installation, what is our homework for tomorrow?
So the homework for tomorrow is basically to install either the Jupyter notebooks or the Google Colab notebooks. So that's the only thing that you need to do for tomorrow. If you maybe read also the documentation to have an idea of the kind of questions that will be and the science that is behind.
Okay, so I think that's our follow-up question. It has no effect on the SCD. I think that's about a gas, if it has any effect on the SCD, I guess, but.
No, I've been writing actually to the people who made the code, and they're just like, how do I put more gas? Because, I'm a Debridis person. I'm not really used to that. And just like, no, you cannot really see that on images or SCDs. It's just lines. So either you make gas lines or you don't, and we did not.
Another question, which maybe I can't really answer here, but is there a similar code to simulate the disk behavior with time?
This behavior with time, including all the gas, the dust, etc. There are a few of them actually. There are some theorists who are actually working on this question. So I'm thinking about Frederick Massey, but I don't know if these are all accessible. Like if they're accessible like this. If you want to simulate the disk over time, you need to include the gas, the grain growth, etc. I'm not sure I'm the most indicated person to answer that questions, but I know that there are lots of people out there doing this kind of thing. I don't know if their code is readily available though. Sometimes it is, sometimes it's not.
Yeah.
But then we might have answers to their questions tomorrow. We're having talks about grain growth and disk evolution. So I would expect they would have more clues about this tomorrow during the talks.
You have some theorists as well, so probably they know more what's out there. Yeah, there was a question, but yeah, to be clear about the hands-on session schedule today, tomorrow. So maybe recap what's going to happen. That today you did the introduction, but what's going to happen tomorrow, maybe.
Yeah, exactly. So today it was just the introduction of what's going to happen tomorrow and give you a little background. And so tomorrow there will be the live session. So you will be provided with the Zoom link. You will be assigned randomly to a room. You will start working with the object that is assigned to this room too. And you will go through your Jupyter or Google Colab notebook. You will try to answer the Google form questions. If you have any problem, you can go to Slack, you can go to your helper. And once you're finished working with the disk, you can go and open another Jupyter or Google Colab notebook on another one. And that will last an hour or so. And after that, if you want to, so 1 hour with the actual Zoom live session. And after that, if you want to go on and on your own, you're very welcome to do so. And we will be there all throughout the week to answer your questions. If you have met some people you would like to go on working with, and you can, for instance, say, hey, let's find one another on Gather in the hands-on lab, like table 4-3, and then you can all find yourselves there and work in a small group, for instance. And at the end of the week, we will have the complete documentation that will be handed to you.
Yeah, I think we're done with the questions. Somebody with them in the chat. Can we work directly with Python? Oh, sorry.
Oh, sorry. It looks like there's one more that's further up. It was upvoted. So, it just, do we know what is the cause or the mechanism of such a large disk gap in PDS-70?
Well, PDS-70 has there are 2 planets in there. There are 2 planetary mass objects in there. So chances are these are at play at digging that. There might be other phenomena at play, but because we're having these planetary mass objects, and also because we've been able to detect them, and direct imaging allows to detect only big objects at the time, chances are like they're quite massive, and so they clear a big zone.
Yeah, and the question in the chat is, can we work directly with the Python which is installed on our laptop?
I mean, I did. Oh, well.
Depends.
It depends. Yeah, it depends. No, I would advise, like, if you have a Python on your laptop, chances are if you open a terminal and type Jupyter Notebook, it will open the Jupyter Notebook in your browser, and that's the easiest way to go, because depending on the updates you've had for your Python, you might have problems. Like, for instance, on my desktop in which I computed all the models and plotted the images, I had absolutely no problem. But when I wanted to do the same thing with the Python that was on my laptop, I ran into lots of problems. So yeah, but I can open the Jupyter Notebook on my laptop, so I would recommend going through this.
Virginie, there was also a question about the colors from table 1 and whether they represent the parameters they need to study for each stage of disk evolution.
So basically, I use the color code like for each object. So everything in the, so you can see, for instance, here for PDS-70, there's orange there, and here the question and in orange. So in the documentation, the question box for HLTA will be lavender, like this. It's just that so that they know when they go through the documentation and all the whenever there are images, I made sure that these images were in boxes of the same color. So basically, when they go through the documentation, they can know readily which object they're taking a look at just through the color. It might be useful for some, useless for others. I don't know, but yeah, that's how I did this. Maybe to increase readability. I don't know if it will be useful for everyone, but it was for me when I put together the document.
Great, I think we can wrap this up. It's 12:30, so thank you so much, Virginie, and everybody ready for tomorrow on this exciting hands-on session. And now we have the poster pops, and Ellen